Hey everyone. Thanks a lot for coming. I didn't know this many people actually survived until Friday at GDC. So I really appreciated it. I was kind of worried I was going to be alone. So when I first gave this talk a couple weeks ago trying to practice for GDC, it was a super in-depth view of everything that we'd done on the rendering side for ACIII. And I think it was a pretty good talk, but it was 40 minutes too long. That might have been a little bit too much for you guys this morning. So I toned it down a little bit. I took out some of the very nitty-gritty details, and we'll do more of a bird's eye view of ACIII this morning. If you have any questions, I'll try to keep time for Q&A. Otherwise, my information is in there in the talks. So you can find me on Twitter. You can email me afterwards. It'll be my pleasure to discuss this with you guys further. So without further ado, welcome to Rendering Assassin's Creed 3. My name is Jean-François Saint-Amour. I was the lead graphics programmer on ACIII at Ubisoft Montreal. So here's a little overview of what we're going to discuss today, which is the major areas of what we did for ACIII. Now the first big topic is weather. We'll also talk about some of our world lighting improvements, our massive crowd system, the awesome ocean rendering that our guys in Singapore did. I'll try to stir up a little bit of controversy with a little rant on node-based shader systems, and then I'll finish up with some of my thoughts on our DX11 version. So weather. Weather was a big deal for ACIII. We knew that we wanted our players to be able to experience all of our main maps in both summer and winter, but obviously this came with many hard constraints. So we had to have the same data set. It had to take the same memory, and it had to be mostly the same performance. Now you can see at the bottom that this is for debatable values of same, but it had to be in the same ballpark so that we didn't have to author all of our maps twice or optimize them twice. So how did we go about doing this? There's three aspects to this that I'll discuss this morning. The first one is atmospheric effects. Then I'll go into surface effects. And last but not least, I'll go into our deformable snow system. So atmospherics. Now we choose to combine all of our atmospherics into a single full-screen quad that is essentially a cylinder, an oriented cylinder attached to the camera, which you can see here on the right. Now the first effect that we integrated into this cylinder is the fog. Previous Assassins had a very basic linear fog system that we choose to upgrade to a height-based and sudden color system. Probably the most important aspect of what we changed was the addition of volumetric mist. So here's sort of a quick overview of our height-based fog system. It's a fairly typical system, I'd say. The interesting bit is this over here, which is the volumetric aspect to it, which is actually a fairly simple technique where we generate the UVs according to high direction versus wind direction, and then we sample a 2D noise texture for the XY, the XZ, and the YZ planes, which we then sum to produce the effect. I'll have videos of this a little bit later on. So now that we have the fog, the second step to the atmospherics is precipitations. We wanted to support both falling rain and falling snow, and we also had to make sure that it didn't rain into partially covered interiors. So how did we go about doing this? The rain itself is composed of two effects. The first one is fairly typical, and it's a local particle system attached to the camera. So this is for the close range that you see. So mostly the rain that you're going to see around our player character, Connor. And then further away, so 20 meters away, is the rain that is inside the cylinder itself. And what we do for this is that we orient the cylinder along the wind direction, and then simply scroll this noise texture along the Y direction. I have a video of this here. So you can see the vertex-lit particles close to Connor, and the cylinder rain a little bit further away. We did something similar for the falling snow, but we could never get the cylinder scrolling effect to work correctly for snow. So we just threw a mass of particles at the problem. So we still have the same particle effect that we have for rain, which is just the falling snow in front of the camera. But when the wind gets higher, we also have two particle systems that shoot snow at your face. And you'll also see large gusts of snow that cross the ground in front of the player. This video over here. So all of this is pretty much just fog and a few particle systems. So now that we have our falling rain and our falling snow, we need a way to make sure that the player can go into smaller, partially covered interiors, and then he's not going to see rain or snow fall through the roof. So for the particles, this is actually quite easy. All we do is do a simple ray cast along the rain direction, and if we hit anything, we fade out the particles. For the cylinder pass, it's a little bit more involved. So what we do is, as soon as we detect that it's raining or snowing enough for the player to start caring about seeing it go through the roof, we disable the fourth shadow cascade so that we have the performance and the memory to render an occlusion mask from the rain direction, and then essentially do a shadow test and block the rain when it fails. This is actually quite a bit more involved because, as you can imagine, by default, the effect is actually you'll see very straight lines. It'll pretty much be the inverse of God rays, and this isn't really what you want. So there's a bit more. It's a bit more involved to get sort of to hide the pattern. So if you guys are interested in this a little bit more, you can just come over after and we can discuss it. So now that we have our rain and our snow, we need the objects in our scene to actually react accordingly. So as you see here, if it rains, you would expect the streets to be more glossy. And this is driven by what we call weather exposure, and it's actually quite simple. Per pixel, we just decided if the world normal points up, you're going to be exposed to the element, and it fades out as your normal starts pointing away from Z up. And as is everything in our game, it can still be biased by vertex color by artists to change the effect a little bit. So how is surface wetness going to impact our materials? It's going to do it in two ways. The first one is it's going to darken the albedo, and you can see this on the left here. It's going to do it particularly for matte materials, which is what you would expect. And it's also going to make them more glossy. So here's the same screenshot again. So at the top, you can see what the street looks like when it's raining. And at the bottom, you can see what it looks like when it's not. It's a similar thing for snow. We do a few things. We fade the albedo towards white. And we also fade in our snow sparkle effect. You can also see here the effect of the artists biasing the weather exposure, like I was mentioning earlier. Normally that street should be all white because it's completely pointing up. But they went in there and removed a little bit of the effect so it would be a little more interesting. And last but not least, our deformable snow. So we actually invested quite a few man-months and even man-years, I would say, into the system. And for good reason, because it's one of the main graphics features of the game. Because it affects both the visual, obviously, but also the gameplay. Because it's deformed by all characters and all animals that we have in the world, which is going to allow you to track them. And again, we needed this to work with very little data authoring. So the snow mesh itself is essentially an offsetted copy of the base ground mesh over which it sits. So here are some references for you guys that might be lucky enough to not know what this is supposed to look like. So how do we go about deforming this? This screenshot should probably give you a little bit of an idea of how we go about doing this. Essentially what we want to do is stamp out triangles of the snow mesh as you step into them and replace them with tessellated and displaced versions of that triangle that used to be there. So we do this by having the player walk around and stomp through a displacement map. As we detect that you step into a triangle, we punch out the index buffer to remove that triangle from the snow mesh, and then generate a displaced and tessellated version of that triangle over the hole that we just created. Now this last part is actually, obviously the hardest part about doing this. And we experimented quite a bit. We started doing this with CPU tessellation. As you can imagine, this turned out to be quite slow when you have 50 guards that spawn in a map and that start walking around all at the same time. Plus, you'll have like 10 bunnies and things like that walking around. So we switched to GPU real-time tessellation, which normally, for current gen, you would not think that that's possible. But it works for us because we don't need dynamic tessellation factors, right? Our triangles are always tessellated the same. So what we do is we use a render to vertex buffer trick, which as input takes the barycentric coordinates of our pre-tessellated triangles, the original triangle vertex position so that we know where to put the triangle, and the displacement map so that we can then tessellate that triangle. And essentially, we're done. Now, if you were going to do a similar system, you're going to run into a few problems. I've highlighted a few of them here just so that it might save you some trouble. The first one is kind of obvious, I guess, is as you're pushing this mesh down, depending on how far you're pushing it, you might actually start seeing the ground mesh below. And you can get around this by encoding the maximum allowed displacement in the snow mesh so that you can then read that back in when you do the tessellation. And as I'm sure you've noticed in the first screenshot, this is a T-junction creation machine. And you're going to see stuff like this happen everywhere. And we have a bunch of ideas of how to fix this. But as a way to get it to work, we just switched to floats. And we actually never fixed it. And it shipped like that. It was good enough in the end, I guess. And that's it for weather. So I'd like to switch over to some of our world lighting improvements now. So I'll go over to an intro of our world light map system, which is the way that we did world lighting prior to ACIII. I'll go over some of the improvements that we did to the system, as well as go over our sort of large-scale world AO system. So what is the world light map? World light map is artist-edited GI, essentially. And this is we've been using this since ACIII, and it shipped ACIII, AC Brotherhood, and Assassin's Creed Revelation. And essentially what it is top-down information overlaid over the map, which is essentially light color and light height and you evaluate that over the map, like so. So it's just a 2D projection of your world space position into the texture. You sample the world light map. RGB is color. A is light height. And then you fade in the color based on the height difference between the light and your current pixel. It is essentially that. Now, there are some pros to this. It's extremely easy to integrate. I mean, I've just showed you what is required. It supports every type of object that we have in our world. And it is constant and cheap GPU cost, which we always like. There are some problems. Since there's no direction information, it doesn't support specular, which wasn't a big deal for previous Assassins because there wasn't actually a lot of specular in the world itself. But now for ACIII, if you think that it can rain everywhere and then suddenly everything becomes glossy, it's a big problem. It's a pain in the ass to author because essentially what artists have to do is paint pixels in Photoshop that they think sort of corresponds to what they want to light in the world, save that, and then see what it did, and then maybe switch the pixel over, do that a few times, do that for a whole 2K by 2K map, and then just crawl under the desk and cry. And then some level designer goes and changes a light post, and they have to go back and edit all of that again. And it's also not great on characters because there's no directional information, and it's essentially, a light cylinder that's capped in the world for each pixel. As soon as you put a character in there, it just smears all over him. So we ended up turning this off for most of our characters in previous games. So World Light Map V2, what do we do? The goal for this essentially was to turn each pixel of the World Light Map into a VPL. And we did this by switching to a two-texture method. The first one is position and light attenuation, and the second one is light color. There's no more artist editing. Now it's sort of real-time generated while the artists edit static lights in the world in the editor. And the VPL itself is essentially our best guess approach at approximating that lighting at that particular pixel in the world. And we simply apply this during the sunpass, during our deferred resolve. And on PS3, it costs 0.8 milliseconds to do this, which is actually very interesting because it gives us 95% of our static lighting at fixed costs. So let me show you some visual comparisons. This is the V1 part of the world light map. So you can tell there's some lighting, but it's very hard to know where it's coming from. And this is V2. So this one with just the world light map contribution. And now with V2. So now that we'd improved our world lighting, we wanted to improve our world AO. Now we already have SSAO in the game. This is a complementary system that provides us with sort of larger scale AO that SSAO doesn't capture. Now the way we were previously doing this, and we've been doing this since ACIII actually, is with vertex AO. Now, there's a few issues with this. The first one is that only static objects can receive that AO. So if you were to put a character, have a character go through between those two buildings that you see here, it wouldn't actually get darker. The second one is that it's obviously it relies heavily on tessellation quality of your meshes, which, as you can see here, isn't always the best. And there's also memory costs. For some of our larger maps, we were budgeting about 7 megs of memory for the vertex, just for the vertex AO itself. So what we did for ACIII is switch to a system that is essentially a world light map AO-based system. So just like world light map, it's a top-down projected texture applied during the sun pass. This means that now all objects can receive the AO. It's about 5% of the vertex AO memory cost. So instead of megabytes, it's a few hundred K for our larger maps. So how do we generate this and evaluate this? Well, it's pretty simple. We just render scene depth from the top view offline, and then blur the crap out of it. And then at runtime, essentially, you do your 2D projection into your world AO map. You do a depth difference, and then you apply that AO to ambient lighting, and you get this. You can tell it's not perfect. The AO sort of fading out as the buildings get taller is sort of incorrect and a little bit weird. But for the cost of the system and the effort to edit the data, it's actually pretty interesting. Massive crowd. Now, what is massive crowd? Massive crowd is a way for us to drastically up the NPC count for ACIII. And there's a few reasons that we wanted to do this. The first one is that our game is based in the American Revolution, and that we wanted to be able to have that, large battles with thousands of soldiers in them. And the second one is that we wanted to go from the standard 100 NPCs that we'd been working with since ACIII to something a little bit more interesting, like 400 or 500. And the reason we wanted to do this, you can see here. Previous ACs were based in old Middle Eastern cities or Renaissance European cities, which don't have large, long, straight streets like we do here in North America. We'd always been able to get away with having streets that were very crooked, that didn't let you see very far, and that hit the problem that 100 people isn't actually all that many to fill up a city. And you can see the problem here. On the left, this is just our regular 100 NPCs, and on the right, it's ACIII as it is now with our massive crowd system. Now, we could actually go, because this is made essentially for thousands of people battling on a field, we could have something like this if we were able to actually fade in real NPCs as you got close to them, which we obviously cannot. So, why don't we normally do this? Why is this a problem? Well, the first problem, and you can see it here, is that assuming best case scenario where you can draw your whole soldier in one draw call, including its weapon, well, if they're shadows, that's 10,000 draw calls. And you haven't rendered your world yet. Now, the typical solution to this is instancing. And if you've ever tried to use any of the instancing API for current gen, they're actually all kind of awful and broken. But as it turns out, you can do this by yourself. So for us, the batch size is 22. And what we do to emulate instancing, I guess, is duplicate the vertex buffer 32 times, include an instance index that you can then access in the vertex buffer to index into relevant per instance data. So like the bare minimum would be position and orientation. Obviously, you can have instant color as well, whatever you desire. And as it turns out, this works pretty well. You have 32 times less draw call. So your insane 10K draw calls are now about 300. There is a downside that you have 32 times more memory. Now, when you think about this, it doesn't seem like a big problem at first because those meshes are normally, they're made to be viewed from pretty far away. At most, they'll have maybe 1,000 triangles in them. But if you have many of them, it adds up quickly. So you have to be careful about this. Now the second problem is that, all right, so we have our 5,000 guys on screen, but they're not moving. Now, traditionally, what we do for this is, skeletal animation and skinning, which then brings you into the question of how do you combine skinning and instancing? Now, regular skinning, say for 32 bones, if you wanted to do it with vertex shader registers, you would need 96 vertex registers per instance, which for 32 instance is 3,072 registers, which is a problem if you only have 256. Now you could do it with vertex checker and it would actually work, but if you care about PS3 performance, which I was told we had to, you need to figure something else out. So what we ended up doing is pre-skinning using render to vertex buffer. This is kind of similar to what we were doing for the snow, where instead of feeding the vertex texture into your vertex shader, you run a pixel shader pass that takes that same texture as input, as well as all of the attributes that you would normally have fed into your vertex buffer. Then you do your skinning in the pixel shader, and you essentially output your pre-skin, pre-instanced vertex buffer directly into memory, which you can then render using your regular pipeline without ever knowing that that thing was skinned or instanced. So this is a general overview of the technique itself. Now, as is often the case, there are some subtleties per platform. The 360, for example, doesn't use the render to vertex buffer technique. It uses the actual vertex sector technique. And the reason for this is that performance is exactly the same. So we just stuck to the simpler strategy, which is straight to vertex texture and skin from there. On PS3, we used the render to vertex buffer trick for a long time, but a few months before shipping, we wanted to get back to GPU performance it was costing us to actually do this on the GPU. So we folded all of the work into a single SPU job that does the skeletal animation, the skinning, per triangle culling using custom edge code, and then outputs that to a vertex buffer in memory, which we can then render. Ocean. Now, the Ocean itself was done by our great guys in the Singapore studio. And in itself, it could be an entire talk. And in fact, it has been an entire talk presented at SIGGRAPH Asia last year. There's also an awesome FXGuard article on how we actually did this. I linked to it in the commenters note, so if you get the slides, you'll be able to get it. Otherwise, if you Google, you'll be able to get the FXGuide article about it. So what I'll do now is just give you a brief overview of what we did, what the different steps are to making that happen. And if you want more details, you can check those out. Now, the wave surface generations itself is based by some pretty old work by Tessendorf, simulating ocean water, and which we've sort of distilled down into a few pretty simple steps, I'd say. So we pre-compute sets of tiling for various levels of waste displacement, which we encode in RGB textures. So we have low frequency waves for our big storm waves, sort of medium frequency for a little bit smaller scale stuff, and then higher frequencies for the microgeometry that we then use as normal maps. And what we do is that we combine all of this at runtime to simulate our ocean and then output that into vertex buffer, which are then rendered. Additionally, we do foam generation. So every frame we accumulate foam, which you see here, I think, yeah. So every frame we accumulate foam from the parts of the ocean that are the most edge on. And I'll show a little bit more information about this later. And then we fade those out as time goes on. All right, so the interesting part. So here are a few layers of the ocean simulation itself. So the first step is just the high frequency normal map that I showed earlier. Then you have the low frequency wave added. So this is just vertex buffer displacement, essentially. The foam, which is generated into a separate texture for everywhere we detect a wave crest is forming. Higher frequency waves, some ambient foam. And then that should be playing for you guys. So there's a little bit more artifacts in this video that you normally see in the game, and that's because we're sort of, very rapidly changing the ocean parameters. All right, now that we have our simulation, let's talk about a little more rendering layers that we then add on top of that. So we have the diffuse, which is very uninteresting. Specular and normal map, which is essentially what you saw in the previous section of just, this is the output of the simulation, essentially. Then we had reflection, which is, I think, the most important visual difference that we have in the game for water. Depth tint, where essentially we have sort of a color gradient which is artist edited that changes the watercolor as the water gets shallower. Refraction and subsurface scattering. And then coastal foam. I don't know if you guys actually saw that, but there's foam that gets added in the rocks and over the edge on the left as well. And the way we pre-compute this is we do similar to the world layer. We do a top-down render, which then gives us distance information so that we can fade in coastal foam. And that, in 2 minutes, is a resume of that hour-long talk, which I encourage you to definitely go into. Now, controversy time. Node-based shader system. Very weirdly enough, this is the most polarizing topic that I discuss with people in graphics. Everything else, people have their opinions, they're willing to discuss. This, they either love it or they hate it, and you're never going to change their mind. And a good example of this is that we've been using this system on Assassin since the very first day of ACIII, and that all other engines that have then forked from Assassins have removed it completely. So let's talk pros and cons. So why do we like ours? Well, the first reason is that it's unmatched prototyping capabilities. Now, there are some good prototyping tools out there for shaders and graphics, but this one allows us to have our own game data and actually our own game. It also gives artists control over their materials, just like they do for meshes and texture. And it gives us a lot of flexibility for custom effects work where we're not willing or we can't invest the programmer time into it. Now, note that we only use this for object materials. Post effects and similar things are still straight programmer-edited HLSL files. Now, here are some examples of this. Now, this might actually ring some bell. This is a cylinder attached to the camera with 3 layers of textures sliding. And essentially, it lets me switch to the other one. Yeah, that was our first prototype of the ACIII Fox system done by a tech artist, completely without us. And we actually used that version in the game for quite some time before moving it to a straight HLSL version for optimization. Now, an example of artistic control over materials. If you look at the windows, you can see that there's some interesting parallax effect in there. That makes the houses at night look a lot less flat. And this, again, was done by tech artists, no programmer involvement whatsoever. And if you've played the game, you'll recognize this as our new out-of-bounds system. This was done by one of our FX artists using our FX system and the shader editor, again with no programmer involvement, which is kind of scary in the end, but it works. Now, this is why that was why we like it. Now, what are the most common complaints that I hear about this? Well, the first one, performance is bad. Memory is bad. And programmers just plain hate it. So let's delve into those a little bit deeper. Now, performance is bad. This can be true, but this can also be true of every single other asset that you have in the game that you probably already have methods to track. And when you think about it, for ACIII, 99% of the pixels that you see on screen are from one of these 6 materials. So single layer, double layer, foliage, vegetation, snow, and crowd. So essentially, that's 6 materials. There's 2 configs really that you're really worried about performance-wise, and that's gbuffer and shadow. So for 99% of our pixels, we have to really look into 12 shaders and make sure that they're as optimal as they can. And they are. I mean, on PS3, single layer is, I think, 8 cycles. 2 layers is 12. Foliage is 5. Vegetation is 4. Snow is 4. Crowd is maybe 12. So I've worked on other scimitar variants that didn't have the node-based system, and our numbers were not lower than this. Now, memory is bad. Again, like other assets, this is trackable. However, I will admit that it can be, like if you let it slide, it can be hard to fix abuses. Because if you end up having hundreds of materials in your game, that probably means that you have a lot of objects that are very special flowers that no other shader in your game can represent. And this can be very time-consuming to fix. So you need some very strict tech art tracking and control over this. Essentially, for this whole system to work, you need, awesome tech art. I think Naughty Dog had a similar talk last year about their system, and they essentially had the same conclusion. For this to work, you need good tech artists. Now, one of the ways that we go about minimizing memory for this is that per material, you get to decide what this can be applied on. So by default, it can only pretty much be applied to regular objects, differ only. That's it. And then you can start toggling possibilities. So can I use this on bulk? Can I use this on transparent objects so that I need to generate all of the lighting permutations? And before you do that, shaders are very small, right? Usually under 50K for all of their permutations. But if you have a very large shader, then you click every single option, and you want their lighting permutations. This could easily get to be more than 1 meg per material. And my favorite. Programmers normally hate this. First reason is complexity. And I mean, it's true. It's going to be more complex than straight up pound defines into an Uber HLSL file. It's doable. It can be well architectured, but I will definitely concede this point. Iteration. Because your shaders are generated by C++ code, it might be a little bit more of a pain to actually change this on the fly while your game is running and have them reload. But it is possible. I mean, it is just hot reloading C++ code. It's more complicated than reloading HLSL files, but you can still do it. And control. Programmers, rightfully so, like control. So let's talk about this a little bit more. Now, what you have here is sort of a zoomed-in view of one of our vertex shaders. What you see on the left side is the output of the vertex shader, and the input is on the right. Now, as you can see in the output itself, it's pretty non-scary stuff, right? Local position, normal, UVs, vertex color, things like that. So this is still independent of vertex format, how you want to do your local to world transform, skinning, how you want to pack your interpolators to the pixel shader. So I'm not clear exactly what control we're actually losing by using this. And it's essentially the same story for the pixel shader. If you look at on the left side, this is the output of the pixel shader. And you'll have normal, albedo, glow, alpha. This is almost sort of like straight into the G buffer, right? So it's still independent of G buffer layout, what you want to do for your lighting, how you want to do it. So again, I'm kind of comfortable with this level of control, in losing this level of control. And finally, our last section, the DX11 version of the game. Now, after ACIII console shipped, we had a few months to work on the PC SKU, which we'd already decided was going to be the first DX11 Assassin's Creed game. So we did the typical things. LOD distance can be much further, loaded area can be twice as big. We have full texture resolution where we had it. Most of our objects we had twice the resolution available because our artists edited twice the game res. We have font tessellation for stuff like the snow. And the two things I'd like to talk about a little bit further is sort of our new high-quality shadow algorithms as well as our new high-quality AO. Now, for the high-quality shadows, the first thing that we did, which I guess is natural, is just say, well, we're going to throw more res at it. So we doubled the console shadow map resolution, which varies across the game and across scenes. But essentially, that means that it can go up to 4 cascades of 248 by 248. And while it does look better, it doesn't look as good as you would expect, or as we expected anyway. You still see some jaggies. There's still quite a bit of noise. And to reduce the noise issue, we went from a regular sort of rotated Poisson filtering to an octagonal filtering method, which essentially tries to approximate a disk filter with no jittering. So it's very simple, stable. It does, however, 25 bilinear taps, so it's not exactly cheap, but this was designed for very high-end PC hardware. So here's a video of essentially how this works. Is it playing? Yeah. Okay. So this is our octagonal filter. The blue and green parts are sort of constant. They're always sampled, and their weights are constant. And the shifting blue area that you see is essentially the pixel moving in light space. This is what gives it stability, really. So this is another. I think this could be a complete blog post by itself. I think I'll probably get around to maybe doing that, because there's a lot more information to be said about this, which really I don't have time to go into right now. So this is just to give you sort of an intuition of how this works. So some results. This is our 16-tap Poisson with already doubled the shadow map res. And this is the new one, which I guess on the projector is kind of the same. But the noise level itself is actually much reduced, and it looks much better when the game is actually in movement. Now, the second thing for DX11 is SSAO. Now, we already have SSAO on console, and we like it a lot because it's very cheap. So a little bit over a millisecond on PS3, but we wanted better quality to be available for people that were going to play on higher-end stuff. So we looked at the typical SSAO algorithms that are already out there. And HBO looks great, but if you want big kernels, performance degrades pretty quickly. MSSAO actually, on the opposite, scales very nicely with big kernels, but the quality isn't quite the same. So what we decided to do was to combine both of them. So we do the first two passes of MSSAO just the regular way. And then once we get to quarter res, we use HBAO instead of MSSAO. Now there are some issues with HBAO for high frequency things. So stuff like vegetation, which you see here, which is a problem. And the way that we get around this is while we're downsampling the depth buffer to do our subsequent SSAO passes, we compute a confidence factor, which is essentially what we determine to be the noise level in Z for that particular group of 4 pixels, so that we don't use HBAO as much when we detect that there's high variation in Z over that particular area, which helps reduce the aliasing a lot. So let me show you some results. I apologize for the image quality. I didn't do the slides on the same version of PowerPoint at this, and it's really doing some awful things to my images, but you'll get the idea anyway. So this is no SSAO. This is our regular console SSAO. So it gets the job done, but it's very subtle. And then this is our MHBAO algorithm. So I'll just go over the masks. This is a regular console SSAO. And this is the MHBAO version, which looks a lot better. Now, the final thing I'll go over for DX11 is just some random DX11 thoughts that I have for you guys today. Now, the first one is deferred context. We use them in the game. You guys probably shouldn't use them. My personal recommendation sources, even though they are getting better, if you already had sort of a D3D9 style multi-threaded rendering algorithm where you were sort of doing your own deferred context, I would definitely advise that you guys do that. I think you're going to be able to control the performance a lot more than what you're going to get with deferred context. Same for D3D queries. Our whole console viz system is based on queries, and on consoles it works awesome. On PC it definitely doesn't. I wouldn't even say that you guys shouldn't use it. It's not even probably, right? Don't use them ever. Even if you do get it to work on one card, you're going to switch to somewhere else or some other card or some other driver, and the performance is going to be all over the place. Don't use this ever. Tessellation. I guess tessellation is the big thing for DX11 that as you start to get into it, it's the thing that you want to use. And in reality, there are really very few use cases for this, especially for artist-created content, especially for current-gen artist-created content. So we use it in one spot, and that's for snow. We could have used it for things like ocean or maybe some terrain. The typical procedural stuff. But yeah, for other cases, it doesn't seem to be very compelling. And the last one is, we didn't the deferred context and the D3D queries, we should not have used this. If we had contacted vendors before, they would have told us this, stay away from that. So, do it early, often. They have good people, they have the info. They probably have some code that you can use in your game directly as well. So yeah, please do contact them. Now, before I wrap this up, I got to come up here today and talk to you about all of this awesome work. And the reality is that I played a very small role in all of this. So I wanted to take the time to acknowledge the work that all of these people did, which really is what you saw today. And finally, wrapping up, I hope you got inspired by some of the stuff that you saw here today. We've talked a lot about next gen this year. This is probably not as exciting. But the reality is that there's 150 million more current gen consoles than there are next gen consoles right now. So they're probably not going to go away very soon. Some of this I think can even apply to mobile, especially some of the world light map stuff. I think that's very interesting. So you have my contact info there if you want to ever talk about any of this or anything else really. And I believe we have time for Q&A, right? So I'll be happy to take your questions. Thank you. Please go up to the mics if you have questions. Yep.
Hey.
Hi.
Do you have made some adaptation for interior, for inside room?
Sorry?
Do you have made some adaptation for lighting on MSSA AO for inside room?
The AO actually works pretty well inside. There are very few interiors in Assassins, so our lighting is very minimal. So usually they'll just use regular different lights to get the look that they want.
Sounds good.
Yeah, just curious. I was wondering, when you're doing the snow and you're saying you do the tessellation for the places where your footprints are going, but
Yep.
you have to pop out the original triangle from the mesh.
Yes.
Do you have any kind of tricks for doing that pop out? Because it doesn't. I can think of a few ways to do it, but it doesn't seem like any are that easy.
Yeah, well, the way we do it is that we just punch out the index buffer, right? So essentially, you can use primitive restart or whatnot for that thing, and then your triangle's not going to render anymore.
Okay.
And that works pretty well for us. I mean, essentially, you're writing a couple bytes. And
Cool. Thanks.
no problem.
Over here.
Oh, yes.
Hi. I just want to make sure I didn't miss this. When you were going over instancing, did you put all the frames of animation for each character in the buffer itself?
No, I mean the animation is still. I mean, we're still doing the skeletal animation on the CPU, right? We're still animating bones, and then you animate that into the vertex texture. But this is per instance, per frame, all the time.
Okay, but then where is all the data actually loaded itself?
The animation
Well,
data?
I'm sorry, not the animation. I guess that's the part that I really want to understand. You said that you duplicated the batch 32 times. What
Yes.
exactly comprises that batch that you duplicated?
Oh, well, I mean, it's per mesh, right? So it's per vertex buffer that you would normally have had pre-instancing. You take that vertex buffer at generation time, essentially, and you make it 32 times bigger, so that if you were to render that, normally you would just render your mesh 32 times at the same spot, and then when you use when you can use your element index that you've put into the vertex buffer, then you can have different positions, and while you're doing this, then your instances will be spread out across the world.
All right, thank you.
No problem.
What was your memory limit for the tessellated snow deformation? And if you hit that limit, how did you handle it if you were basically destroying the original index buffer?
Yeah, I think we had 2 megs reserved for the tessellated meshes. When we did hit that, we were sort of, bringing the distance where we would allow tessellation. So essentially, we'd just remove the tessellated patches that were further away from you, and we would, bring back the original index data into the index buffer.
So was that streamed from disk, or did you have a separate copy of the original undestroyed index buffer?
No. I mean, every triangle patch. I mean, when it destroys its index buffer, it sort of remembers what used to be in there, so that it can put it back when we kill it.
So you mentioned that instead of using the DX11 deferred context, you use the DX9 multi-thread instead.
Yes.
I'm wondering what are the specific problems you saw so that you come up with this recommendation.
Our issues mostly is with performance.
Okay.
You will see, depending on which vendor you're running this on, you will see that deferred contexts actually don't do a lot.
Okay.
So
is it like a per card variance so that?
There's a card variance, there's a vendor variance almost, but I mean, across vendors, I would not recommend them. I mean, because they don't do as much as you would like, right? Essentially, you would like them to do something similar that when you have on consoles, which is, you're actually writing command buffers on the deferred context. And that's not actually what they're doing, right? They're just sort of queuing up commands, and then they'll create the command buffer on the main thread. So the performance characteristics of this are essentially the same that you would do if you did your own sort of D3, D9 multi-threaded, which is what you would be doing.
Because I heard that basically all the display card vendors, they are trying to, up to this point, they were basically emulating the deferred context.
Yeah, well, NVIDIA has real deferred contexts.
Yeah, so going forward, that might be better. So
it might be better. I mean, from what I understand, you will still pay very large validation performance of this in the driver. So when you submit the command lists, there's quite a bit of validation that they have to do in the driver.
Okay. Because
D3D forces them to do it, which you would not have to do if you were doing it yourself.
Okay, thanks.
I may have missed it. Were you doing depth culling on those cylinders that are wrapped around the camera, or are you doing the blend yourself? How do you avoid lines and missing effects near the
essentially it fades out top and bottom, but I mean it is sort of blended in the scene, reading because to do the fog itself, it has to read the linear Z already, so it makes sure, just like soft particles, it makes sure that you don't see the seams.
Perfect, thanks.
Anyone else? All right, thank you.